All right, swirl.
All right, considering you have a test in 2 days, any questions from chapters 1 through 3? Or questions about old tests or anything?
Are we gonna have a cheat sheet with like where we can put down the equations and stuff, or is that gonna be on the activity?
The equations, basically I did a cut and paste of the equations that are at the top of the quizzes.
Okay.
So that's what you'll be given. Any other questions? All right, let's pick up where we left off. I believe we just talked about friction and the formulas for friction. And I don't think we actually went back and solved it with friction involved. What was the angle?
30 degrees.
30.
And did I give you coefficients of friction?
Yep, kinetic is 0.2, static is 0.3.
0.2 for kinetic and 0.3 for static?
Yep.
And there we go. All right, so going through the process, force diagram, already done. We did that early on, a couple weeks ago, as well as last time. Acceleration is still going to be, if it's going to accelerate, it is going to be down the ramp. Coordinate system, same as before. We want one of the unit vectors to be in the direction of acceleration, the other one perpendicular to it. And so, decomposition. I need to break up any vector that is not in the positive or negative I hat direction or positive negative j hat direction. So are there any vectors I need to break up?
Yes.
Which one?
Weight.
Yep, just like before. Friction's a negative I hat, so it's good. Y is a negative j hat, I'm good there. Weight gets broken up. And it's the exact same as before. Down the ramp is W sine of theta. Into the ramp is W cosine of theta. And then we have normal force and friction. So that's the decomposition. Now we're left with the equations of motion. Again, our template, the thing that basically sets up how we write our equations of motion, is Newton's second law of motion. The fact that force is equal to mass times acceleration. The emphasis of the lab that we're not doing today. And I'm going to have two equations of motion because I have one object in 2 dimensions here. Okay. Someone want to take a shot at one of the equations of motion?
Would the I hat be W sine of theta equals MA?
Close. You left one thing off.
Minus friction?
Minus friction, yeah.
Okay.
I also have friction this time. So minus friction is equal to mass times acceleration. All right, the j hat equation. Someone want to take a shot at it?
Weight cosine theta minus normal force.
Other way around, because I defined j hat to be that way, normal
Oh,
force
I
would be
see.
positive there. Ultimately, in this particular problem, it would not have any effect, but still. Equals,
MA.
we can do better than that. All right, if I write down MA, the issue is I have these two A's right here. We're claiming that the acceleration in the I hat direction is the exact same as that in the J hat direction. Is that the case? I got a couple people shaking their heads no. Then where is it different?
It's not accelerating the J hat direction.
That is right. Again, one of the reasons we choose our coordinate system the way we do is so that one of these equations equals 0. Now, sometimes you can't help that, but it's preferable if you can do it that way. All right, so those are the equations of motion. Substitution. Now we have two equations that are independent of this, which we can do substitution. So we have an equation for weight and an equation for friction. What is the equation for weight?
Is it mass times gravity or little g?
Yeah.
Whatever you want to call it.
mg works. Acceleration due to gravity. It is indeed mg. And friction, again, we have two types of friction. We have kinetic and static. I think this is sort of how we ended up the class. So kinetic friction has a very definite equality here. That's equal to this coefficient of kinetic friction, which is materials dependent, times the normal force. And then we have static friction.
Less than or equal to that.
Yep. Because static friction is always going to be enough to keep it from sliding until you hit that breaking point. So the question is, are we going to hit that breaking point here? Well, with enough experience, you can look at it and go, yeah, we're going to break it, or no, it's not, or I'm not sure. But for right now, let's just assume that we don't know whether it's going to hit the breaking point or not. So what we're going to do here is we assume we're at our maximum static friction. So step one, so we're dealing with friction. One, assume Fs max. I'm going to plug in mu s times the normal force. Then solve for acceleration. Is object sliding? And then if yes, friction is equal to kinetic friction. If no, then acceleration equals 0. This is the essence of these problems. Potentially you're solving it twice, depending upon what answer you get from the first one. Not sure how far over I can go. Okay. So we assume we're at the maximum static. If it's not sliding, it will become clear. And so let's go ahead and do our substitution. So I have mg sine theta minus mu sy is equal to ma. For my second equation, I'm just going to go ahead and move w cosine theta over. I have y is equal to mg cosine theta. Now, even though you could plug in numbers early, we could have plugged in numbers actually when we wrote down our equations. It is beneficial in a problem like this not to write in the numbers until as late as possible, because it becomes a whole lot easier. If I have to redo the problem with the kinetic coefficient, It's a lot easier if I just have the equation to plug into. At this point, I have a formula for normal force for this problem. I can plug that in. And so now I'm left with mg sine theta minus mu s times mg cosine theta equals ma. And so, can I simplify this at all? Or how do I simplify it?
Divide both sides by mg.
Or just m.
Yeah,
There's
yeah,
no G
I'm
over
sorry.
here, so no
Yeah,
advantage to that. All right, so we divide by m, m's go away. And so now I have a formula for acceleration for this problem. My acceleration is equal to g sine theta, which was the acceleration when there was no friction, minus this frictional piece, us g cosine theta. At this point, we can plug and chug. 9.8 times the sine of 30 degrees minus 0.3 times 9.8 times the cosine of 30 degrees. So this is 4.9 minus somewhere around 2.2. Closer to 2.5, about 2.543611. So it's going to give me a real number.
I got 2.54611.
Whoa! For this part right here?
Yep.
Ah. I'll consider that a victory. And then the final answer?
2.3538, or 3539, sorry.
All right. Units?
Here's the second square.
Usually without the question mark, but yeah. All right, so we have an answer here. The question is, have we reached our final answer? Is this the acceleration of the mass? Don't forget, we have assumed we are at using maximum static friction here. Did this overcome the maximum static friction? Have we overcome maximum static?
No, 0.3. Yes. Yes, we have. It's 0.3.
So why are you saying yes?
Because static's 0.3.
That's where this number came from.
Okay.
Remember, 0.3 is unitless. That's not friction itself. That is just
Gotcha.
a number. All right, so we put it on the ramp there. We say it's going to, working through with a maximum static, we say that it's going to accelerate 2.3539 meters per second squared. Is a positive or negative number
Positive.
is, and we said positive was down the ramp. Does it make sense this thing's gonna accelerate down the ramp?
Yes.
The fact that this is a positive number tells us that, oh, we have overcome it. The other way of looking at it, this right here, that is the force pulling it down the ramp. This right here, that is the maximum static. We definitely overcame it. We have more down the ramp than what's trying to hold it back. So therefore, it will move, it will slide. Therefore, kinetic. And so this is the advantage of not until waiting until the end to plug in numbers, because the only thing that changes,
0.3 to 0.2.
yep, this, you go back a little bit further, we put a K there, put a K there, K there, and then as Craig said, the 2 there. So 1.6 something.
1.697.
Point.
203.
That is the acceleration down the ramp. Questions before I change the problem? Okay. So let's change the problem. Let's change the angle to 10 degrees. Maybe that's enough. If it's not, I'll change it again. So I've changed it to 10 degrees, so the question is it going to slide? So let's work through that again. I don't have to change anything else other than it's now an S instead of a K again. I'm just squeeze an S in there. S. So I've lowered the ramp. So what do I get now?
9.8 sine of 10 degrees is 1.702. Minus 2.895.
All right. So working it through this way, by just changing the angle, we have a negative acceleration. Physically, that would mean this thing is going to accelerate up the ramp. So it doesn't make physical sense that I have a ramp here, I put a mass on it, and suddenly the thing's going to accelerate up. I would like to see that. I'm hoping none of you can imagine it realistically happening, that I put a mass on a ramp and it will suddenly go up the ramp. That negative sign means I have not exceeded my maximum static. Because remember, we're using 0.3 here. That's my maximum static friction right there. That is the force that's trying to take it down the ramp, and therefore it will not slide. Therefore, I already know the direction. What is the acceleration of the box?
0 meters per second squared.
Yep. All right, questions here before I make it more complicated? All right, let's make it more complicated. Let's make this, 6 kilograms. Let's make this 8 kilograms. All right. First step is
Force fiber.
so we're still in the beginning stages. We'll go ahead and do the full thing. Assuming the ramp is part of the earth, I did not draw it as a separate drawing. All right, we have our checklist here. Tom. So tell me a force acting on what, in which direction?
You have tension from either end of the rope, going directly to the box 1 and 2.
On the rope?
Yes.
So it might be a rope.
And then from where it meets the box, going back towards the rope.
Okay. Tension's done. One rope, took care of both ends. Any other forces? Is that it?
You have friction, going up the ramp, opposing the direction the box wants to travel.
Which way is it gonna go?
For box 1, it's gonna go down the ramp.
Box 2's going up,
Yes.
based upon? Feels right?
I'm basing it on the weight of the box.
So I got the more massive one on the right, with a lower angle. Alright, so this is one of the reasons why I did this problem, is which way is friction going? Now, Brandon could be completely right here about which way it is. You might have just the good gut feeling of which way it's gonna go. However, let's assume, so this would be, you don't know which way it's gonna go. Let's assume no friction to start with. We'll bring friction in afterwards once we know which way it wants to move. So I guess step 0, tacked on to the ones I had up there before, assume no friction if desired direction of movement or of slide is not known. So we're going to ignore friction for right now. Friction on hold. All right. So we got 3 other letters to deal with, O and G.
Your normal force is acting, you've got it acting on each box, but it's perpendicular to the angle on the box, away from it.
Okay, away from the ring.
Yes.
So I'm gonna call that Y2, Y1, Y1, Y2. For completeness, we do have 2 other things that are touching. There's another pair of normal forces.
The rope and the pulley.
Yep. So, and then I got Y sub P or R, whatever letter you want to use. Y sub P. All right. Ultimately, only the forces acting on Y1 or mass 1 and mass 2 are the only ones we really care about for solving for acceleration, but just a little exercise and other stuff.
You have gravity pulling both box 1 and 2 down and the ground up from you guys.
W2, W1, and then W1, W2. What about other?
The rope and pulley.
What about rope and pulley? Is it weight of rope and pulley or weight that does fall under the other category?
I'm not sure.
Other would be if there's a force that I mentioned in the problem but didn't really say where it comes from. No, yeah, there's no other in this particular problem. All right, so what I care about now are my 2 masses here. So I'm going to take my mass 1. For the sake of notation, I'm going to call 30 degrees my theta 2, and the other one's theta 1. So I have normal force acting this way. I have weight 1 acting down. I have, oh, that's Y1 there. And then tension acting up the ramp. And then for mass 2, I have weight 2 acting down. Y2 acting this way and tension acting this way. So we've done the force diagram. Acceleration. We don't officially know which way it's going to go. Brandon seems to feel that it's going to go this way, mass 2 is going up and mass 1's coming down. Just for the sake of argument, let's just assume going the other direction. This is not to be contrary, but I'm hoping he's right, and I want to show what happens when you pick the wrong direction. So we will assume acceleration this way. Because friction's not involved, it's simple if we have the wrong direction. So we set up our coordinate system here. I 1 half, J one hat. And over here, I two hat. And what the heck, J two hat into the board. Or into the ramp. What do we need to break up? Decomposition time.
Wait,
Yep. And we've done that before, so we can just jump straight to it. So taking my diagram here, I got tension acting up, normal force perpendicular. Down the ramp is W1 sine of theta 1, and into the ramp, W1 cosine theta 1. Over here, I have Y2 up to the right, tension up and to the left, W2 cosine theta 2 into the ramp, W2 sine theta 2 down the ramp. And now, equations of motion. How many equations of motion will we have? Now let's do it by democracy here. I will just go ahead and say it's not more than 6. Who says no equations of motion? I want you to have a number in mind. I want you to vote. There should be 10 votes total here. Okay. Who says 1 equation of motion? Two equations of motion. Good one for that one. All right, so I got 2 people there. 3 equations of motion. 4 equations of motion. I guess, Amaji, what are you going for? 4. Democracy works. It is 4. Why is it 4 and not 2? For someone who said 4, they got 7 people here. One of you, I assume it's more than just divine inspiration.
Each box is gonna have 2 equations of motion for each direction, so there's 2, that'd be 4.
Yep. 2 objects, each have 2. All right, so we'll have an I1 hat equation, we'll have a J1 hat equation, we'll have an I2 hat equation, and